Okay. So first I share the screen. Okay. Can you see the slides?
Yes, they're there.
Okay, we go on. This is just introductory slide. Very fast. Kernel. We are talking about the Unix and Linux kernel as a prototype of a simple kernel. That this discussion is about the general characteristics. I think that of most kernels, non-real-time kernels, not dedicated real-time kernels, including OS X and even Windows. So these are absolutely the basic concepts that in common, and they are related strictly to the Unix Linux architecture, and this is important also because Linux is widely in use in embedded systems, automation systems, and robotics in particular. So the kernel, we are talking about the kernel that is always resident in the machine. You know that there are two modalities in which every processor now at the hardware level works, as to say, kernel mode and user mode. The kernel mode is a hardware configuration in which the code that is working, that is running, the kernel in particular, is able to control completely the machine and execute any kind of instruction, because there are machine instructions that are reserved to the kernel mode. The user mode is the modality in which user programs run, and there are limitations. User mode cannot access the whole memory, cannot access in general the hardware addresses, so it is impossible for a program compiled and executed in user mode to access directly the memory addresses that map the peripherals in general. And they cannot execute any kind of instruction, so you cannot run a kernel in user mode, because the kernel needs some special instructions, in particular related to hardware and not only external hardware, but also internal, the memory management and so on. So the two modalities are different. Kernel has the total power about the machine, user is limited in general. What is a process? Well, this course, the ARP course, focuses mainly on processes and threads. In this architecture, the simple architecture, the Unix simple architecture, processes and threads are basically the same thing. They are entities, they are scheduled and run in time-sharing mode, we will see. You see here that the concept of thread is related to the idea that they are lightweight processes. Well, I forgot to say that I've made some small changes, but in most cases are mistypos. So few errors, not very relevant. In the first version I uploaded in our web. So this is the new version. If you want to have the corrected, completely corrected version, please download again. The code for the processes usually does not reside in main memory, can be swapped out from my main memory. This is common and useful when you use your desktop or a laptop and so on. Not very frequent in automation and robotic applications in which your processes usually need to stay resident in memory. It's just a performance characteristic, not nothing has to do with the logics of the processes. Another key issue is time sharing. And this means that time sharing is opposite to real-time scheduling. Modern Linux operating systems are so fast that usually in many applications you don't feel much difference between a true real-time and a time-sharing system, because also time-sharing systems like the one I'm using now are so fast in reacting that you can't consider it in real-time. This is not true in general. Windows is not real-time. You can perceive the difference when you use multimedia streamings and voice images and so on in general, not related to robotics. But the idea is that any process runs for a quantum of time, and then the CPU and resources go to another process. This is the idea of protections of the kernel mode with respect to user mode. I'll go quickly. You can interrupt me anytime you want, of course. This is important, really important, and is common in every operating system, modern operating system, even in Windows. The process ID. Each process is identified by a number. It's very simple. Just unique number is integer number or is a natural number, starting from 1. 1, 2, 3, 4, and so forth, on and so forth. The number is unique. And for security reason and safety reason, processes have owners. Usually the concept of owner is strictly related or with the same concept with the user of the operating system. So users are identified, single users, and a user and processes run by a user are owned by the user himself. A user itself, himself, herself, has a user ID, that is again a natural number, and also user can be grouped in groups. So we don't use that, so we skip. So this is the kernel. And this slide, so this picture is, we will meet this picture several times because we will analyze single components of in this picture. So far we know that there's a kernel, and every time the kernel runs in kernel mode, and there are processes. So the lower side is the part of the user process, and there are peripherals. Pictures are old style, but in any case are peripherals. We should include also motors, laser scanners, cameras, and kind of hardware. Many processes. So the idea is that we interact with the kernel, with the peripherals, and any other actions in the concurrent distributed program that we know is the goal of this course, using system calls. The system calls is a routine calls or a function call inside the kernel. So this is very important for us. We will spend a lot of time on this. This is a call, and usually a system call generates an interruption. In this case, the system call seems to have the purpose of writing on a disk or reading from a disk. So the peripheral, in general, except for a very reduced number of situations, a system call generates an interrupt. You will see the concept of interrupt that unifies external hardware interrupts and internal interrupts. The interrupt goes back and usually stops the process. The same happens when you use the system call not for communicating with the hardware, external hardware, but also for communicating inside the cloud of processes. So this is the what we call the inter-process communication, and is in any case carried out by a system call. So we will talk from now on, just after the description of the operating system, we'll discuss some system calls. Our world is made of system calls to do anything that cannot carried out by simply the simple computation of a sequential program. If you have to compute to make arithmetical or logical computation, you don't need system call, except when you want to write or read data. But for us, the important thing is just to communicate with other processes, to synchronize in time and through events and so on. We skip the process group, kernel and process. So we have already seen this. We go on. Sorry, it was the wrong click. Okay, system call. System calls in general are three kinds: input-output, process management, inter-process communication. So anything, including sockets. Well, inter-process communication are different kind, and they implement at the lowest possible level the concept that we have seen in the first class, as to say the push, pull, blackboard, publish, subscribe. That we have a very limited form of publish, subscribe in this this level. Inter-process communication includes also external communication using the network. So socket is the name for the communication. But generally, we include in the inter-process communication, since the idea of process here is not related, strictly related or limited to same machine processes in the network or in the world connected through the internet. So when you communicate with another process, you can use several kind of communication, and socket in general is used for outside processes in the network, but can be used also for inside processes in the same machine. We go on. This is the standard of the Posix in general. Posix can run in any machine, any Posix compliant machine, with this concept of portability through recompilation. Different kernel, same interface, system call Posix. So the Posix is exactly in this level. It usually is a dotted line that separates the user space and kernel space. And this dotted line is the Posix interface. But in any case, you have to recompile your code. This is the Linux version, so not very important. Posix has several extensions. So Posix is a subset in general of system calls available in your operating system. And if you use the Posix subset, you're sure that you can port your software. In many operating systems, including Linux, there are other system calls that are not Posix compliant. And we will see just one, because it's important to be aware of that. Go on. Daemons is an old term born within the, was decided by the UNIGE designers in the years 70s of last millennium. Presently is not widely used. Usually they're called services, but in any case are services. System processes, and many daemons run in user mode because are not part of the kernel. So they have to access the kernel using system calls. Some daemons are inside the kernel, for example, the memory management and swapping between memory and secondary memory at the hard disk, for example. No, I'm sorry. Okay. Everything I'm asking, is it clear? Questions about that? Are you connected?
Yes, sir. Yes, sir.
Okay, sorry. Okay. So we go. Today we will have 3 moments in this class. So I will go fast and analyzing and commenting the slides. And then we will have 2 different moments with different topics inside. So with a small interval inside. Go back to, no. Okay. I want to stress the fact that interrupts, the classic interrupts, coming from the external hardware and internal events that we will see are absolutely the same. So it is important. Modern kernels act in this way. They do not make any difference. System call. In this case, there is a program that is running. syscall, I think the 2 L letters are being transformed in I, doesn't matter. Syscall with parameters. Parameters is a function call, so we have parameters. You run your program. As soon as you issue a system call, you jump in kernel mode. So the process is temporarily suspended and the kernel runs. And it raises an interrupt inside the kernel, just like an interruption from external hardware. The dispatch vector is the hardware low-level system to distinguish between interrupts. So it's an interrupt, like any other kind of interrupt. It is a special interrupt reserved to system call. System calls generally raise few interrupts because after the call, the kernel distinguishes which kind of system call it is. So the dispatch vector is the internal mechanism to distinguish and to run the proper routine body. That means that is an old term, old terminology. Interrupt routine is a function inside the kernel connected to the interrupt and is carried out. Immediately after the execution of the routine, maybe the system call is just for for example, we will see the next step we will see is just a system call for running a new process. Running a new process. A process in execution decides to run a new process. We will see the mechanism is called fork. In that case, the routine is just the execution of the fork. The new process is generated. Immediately after the execution of the routine connected to the interrupt, the software interrupt in this case, is activated the component of the kernel that is called the switcher. The switcher is the most important element of the kernel. The switcher, probably, but not necessarily, we will see, returns the thread of execution exactly in the point where the process was interrupted because it did call the system call, the proper system call, and the execution continues. So from the point of view of the algorithm, you don't perceive any interruption, but just only the effect of the system call you have called, maybe any kind of system call, of course. But there is the switcher in the middle. The switcher not always returns the execution to the process. Sometimes does some other, takes another decision. For example, and in general is the most frequent decision is to stop temporarily the process in execution and to run another process. We see the concept of scheduling. 99% of situation when you issue a system call, when so you call a service from the kernel, your process is stopped and another process gain the CPU and resources. This is made by the switcher. So the switcher is the scheduler component and is a passive routine, is a function itself. So you don't think of the operating system with as a running program that continuously wants to schedule a new process. It's just a passive decision. As soon as you return from an interrupt routine, the switcher decides which is the process that has to be run. This is an example, a detailed example, skip it. So, what are interrupts? Hardware signals generated by peripheral devices, generated by CPU in case of exceptions of any kind. Typical division by zero that any nearby programmer finds sometimes, but maybe any kind of error. Software interrupts are the third category, the one we are dealing now, because we are interested in system calls, and any system call generate system calls. They generate interrupts. An interruption causes the control to be transferred to the kernel, and so on and so on and so forth. In this case, so just to impress in your mind, in your memory, that in that case there's no system call, but simply an interrupt. The interrupt occurs asynchronously anytime. In that case, you jump in entry point, interrupt vector, interrupt handlers, switcher. In some cases, you go back and continue the execution. And sometimes the switcher decides to give the resources to another process. So it's just a resume of any of how an operating system works. We must be aware of that, because the system call always, not always, but many times asked to be aware of the management of the interrupt. We will see there are system calls dedicated to raising an interruption so that another process is aware of the interrupt raised by another process. So two processes communicate using interrupts. In this case, that's called in general events, and is a form of communication like the publish, subscribe, or Blackboard, and so on, but with no data exchanged. So, and in real time, and in real-time programs, even not strict real-time, concurrent programs for moving the hardware of the robot, events are very, very important and frequent. And there is a mechanism that we will see that is called signal. There is a special message that is just managed using the concept of interrupt management. So this is concept of different things. Doesn't matter. So far, we are still in the same drawing. I think we need a dotted line. Dotted line. Okay. Nothing new except the fact that now we have a look. We have a look at what is inside the kernel. So far, it was just a rectangle with written kernel. So the component of the kernel are the switcher, system calls, interrupt handlers, input-output drivers. In this course, we will not talk about input-output drivers. Input-output drivers are just small routines connected to the peripherals that allow you, using a proper system call, to access what is not accessible for a normal user, as to say the the memory locations of the peripherals. There are special memory addresses, usually lowest addresses, that are connected to the hardware for input and for output, and they are not accessible by normal programs. You must issue a system call, and you have a routine written inside the kernel that carry out the interface. There will be, I think they are presented in the real-time course. So aside the user processes, we have also, we see now also daemons, as to say, the services. They are user processes that runs automatically. They're usually run directly after bootstrap. Scheduling. Okay, scheduling is the concept managed by the switcher. The switcher, when we said switcher gives the control of the CPU and all resources to another process, has to do with this general scheme. States. The concept of state is self-explaining. A process is running when it has the CPU and is just running, executing instructions, and sometimes also system calls, so interact with the kernel in some way. Another state is a process that is not running. In Unix terminology is called asleep or sleeping. A process is sleeping when it has no controller of the CPU, is doing nothing, because there are logical conditions that are waited for. Logical conditions are just waiting for events. The normal, the classical example is just waiting for an input output, but maybe waiting for an internal event, for an internal interrupt, for a communication to be completed with another process and so on, but also having space, having room in main memory. So the process can be swapped, suspended, and put in the disk. Not common in robotics and in automation in general. And so is waiting for the logical condition to be loaded again in memory. So a process in the sleeping state cannot run, cannot. But when the event occurred, the process in a sleeping state becomes ready. Ready is simply a process which has no reason for not run. But if you, in general, we have less CPUs than processes to run. So connected to the really conceptual state, there is a queue in which many processes are ready to run. Who is the component that changes the status of a process from ready to run? Is the switcher. The switcher, as to say in general, the scheduler. The process is the function with an algorithm that decides as soon as an event occurs to switch a process from ready to running. This is the reason why I told you that 99% of in cases when you issue a system call, the process is taken out from the running status and goes asleep, because a system call in general needs some time, and when the system call is completed, an event, system call completed, occurs, and so in this case you can put again the process in ready state. There is an automatic mechanism, a lowest level mechanism in Linux in particular, in all time sharing systems, in which also a process is changing from running to ready, also when the time quantum expired. Because time sharing, by definition, says that you cannot run indefinitely. After some times, you must be stopped. So it's a lowest level mechanism, usually carried out, not usually, always carried out by the switcher. The switcher simply, after some times, there is a timer, that is an hardware timer that sends interruptions, and when the interruption says your quantum is expired, from running you go to ready. Why to ready, not to sleep? Because there's no reason to wait for a special logical situation for some event. It's just an internal switching between the two, swapping or switching between the two states. Okay, process switching occurs. This is exactly what I said.
Professor?
Yeah?
I have one question.
Yeah.
Is there a possibility that the two states are functional at the same time?
No.
Okay.
The idea is that any process can be, just having a look inside, not very important, but in more details, you will see also that there is a table inside the kernel that has a unique coding of the status of a process.
Okay.
This is a sort of axiom. A process can say just in one state. The scheduling is carried out by a switcher. There's a jargon that says CPU bound processes and input-output bound. CPU bound means that a process uses only CPU for computing, or mainly CPU. And this is the case in which quantum of time, the quantum of time decides that you have computed for such a long time that you must stop it and go back to the ready state. Processes I/O bound, those processes that carry out a large amount of input-output, so they are suspended by interrupts, not system calls. Input-output includes also the concept of inter-process communications. So in general, those processes, input-output bound, are interrupted by the system calls, not by the quantum of time expired. Yes. Well, the logic. So I think they can. Well, I suggest you suspend for 5 minutes. And so we will finish the first part of the slide. Is okay for you? And so we talk of priority and processes, and we will see, okay?
Okay, see you in 5 minutes.
Yeah, 5 minutes. Stop share. I'm sorry because I didn't decide that. It was just, I stopped my video so you couldn't see me, but probably it was better not to see me. The next time you will see. I stop recording. 5 minutes. Recording is on and we go on. Okay, priority. In the going back just for a while here. Priority is related to the ready queue. Usually many processes are in the ready queue and the switcher has to pick up one. The policy for picking up one of just one and making it running is just what is called the scheduling algorithm, scheduling policy. The time sharing policy is probably the simplest one, but it needs, in any case, some details. And in general, the mechanism for choosing deciding the process to be switched and to the running states is based on the concept of priority. You will see in the real-time algorithms, real-time schedulers, and in proper real-time kernels, not the standard Linux Unix kernel, priority is used in a wider sense and with decisions that are really more complex than this. In this case, we have to just decide democratically or and pragmatically, which is the best way of deciding how to switch off and on a process. The Linux kernel has a priority level that represented coded in integer numbers. With the lowest number is, I think, -20, if I remember. It's not important, but the idea is the highest priority is the lowest number, the negative number. So positive numbers have a lower priority. Processes running on behalf of the kernel have, in any case, higher priority than user processes. So any process has a priority. The priority is dynamic. So the idea, the algorithm is based on the idea is that the priority assigned to a process, in general, a process starts with a given priority that is equal, but can be changed, slightly changed. But in any case, start, for example, 0, And during run, the priority changes. The number raises, so the priority is coming lower and lower. When two processes have the same priority in the ready queue, the choice is made on the idea of the round robin, so given the same probability to any process. the priority changes. This is the formula. The base is the initial priority when you run a process, for example, 0. And as soon as the process uses CPU, the priority increases, so the real meaning of the priority decreases. You can start the process with the initial privileged priority using a command that is reserved to the super user or the administrator or the kernel itself. So as soon as the process runs, as soon as the process gains a priority that is lower, a priority of some ready process, the running process is switched off, and the ready process with the higher priority becomes running. That's the end of the first pack of slides. So now what we know, we know that there's a kernel space, user space. Kernel has access to all the hardware and all reserved instructions. Kernel code has always a priority higher than user codes. User processes can just run, but as soon as they want to interact with the external, with the peripherals, or want to interact with other processes, or want to run new processes, they must issue a system call. System call is interfaced with the kernel. Everything is managed by a system. Yeah, okay. Sorry, there's an information coming from outside. Everything that is not everything except just logical and arithmetical computation is managed by system calls. Everything. And we have seen the system calls raise interrupts, software interrupts, that are managed by the kernel exactly with the hardware interrupts. We can include in hardware interrupts also interrupt raised by some errors inside the execution. Those of you who know C++ or Java know that is the mechanism of catching exceptions, and exceptions are exactly software interrupts raised, well, hardware interrupt raised, for example, by division by 0 or something like that. And so there's a unified mechanism interacting with the scheduler, or better, the scheduler is just powered by interruptions that may be software interruptions, internal events, external interruption. The switcher is in charge of deciding any interruption arriving, or if the process has to change status. The time sharing or mechanism of based on the priority and quantum of time is just another mechanism powered by the timer interruption. The timer is simply an hardware clock. Kernel now, I think that Linux kernel runs at 10 milliseconds quantum time. That is, as to say, the internal clock just sends an interrupt every 10 milliseconds, maybe less if your CPU is faster, 5 milliseconds, for example, and the switcher decides to change the running process. So this was the first part. We have a second pack of slides that is and with the second pack of slides, we will finish the description of the sample, let me say, kernel, in particular the Linux kernel, and I will upload in our web now just after the class, and I will ask you to read deeply read and understand before next week. So next week we can finish the description of the system with all basic concepts that are important for understanding the system calls. So, second topics of the day. Second topic of the day. Time is okay. The second topic is strange topic, but I want you to show something in advance, just so to have. I will show you a program, and even if we don't know exactly which are the system calls, which system calls we are using, and so on, I will just describe in practice just one, just to have an idea of, and this is also an example of the exercise we will do and the exercises that you will be asked to do by yourself. So maybe it's a shock for someone other, maybe just very simple, but I think it's important just to show, since this in this second week, to share the screen and which is the LibreOffice. Okay, this one, fantastic. I think it's too small. Okay. No, I will change. Sorry, I cannot. This window is too small, so I have to do stop share, stop recording for a while, pause recording, just wait. So 1 minute interval. Now it should work. Fine. What is that? In my experience, for some of you, it's a shock, but it's just a Linux or Unix shell screen. So the interface is not the classic graphic interface. We have to write commands. This is the prompt. We can do, the ls command is just listing the current directory. In extended form is this one. And we see, well, to write small programs in this course, we need to use the shell and the compilers, not in a
Hello, sir.
Yeah?
I have a question.
Yeah.
Can we get away with using Linux on Windows for this course?
You should use Linux. Linux. Well, there is a Linux subsystem in Windows in Windows 10. But so we have the shell and it's complete Linux, but it's not fully compatible because not all system calls are implemented, because the internal mechanism for communication is not completely supported. Probably next year the WSL, Windows System for Linux, will be a full Linux, or maybe in this during fall, I don't know, but it requires a machine with the capability of total virtualization. So is not running in all Windowses. So I've tried several Windows subsystems, and I strongly suggest you to run a full Linux in virtual machines. Very simple.
Okay, but I can use the one in virtual machines.
Yeah, using virtual machine, I'm using the 18 distribution of Ubuntu. The exercise we are carrying out are also in Red Hat or in other distributions. I use that because it's stable and simple. So,
All right, thanks.
okay. If you using the OS X, using the Mac computer, you can also use the shell, but I'm not sure that all system calls are implemented in the same way. So I suggest also in this case to use a virtual machine. That is very simple and easy and completely free, like VMware, of course. So here is a shell. You'll be familiar with the commands of the shell, but in exercise, I will show you also the 10 commands that you must use. For editing programs, you may use the normal interface with an editor of any kind. I'm an old programmer, so I use the old editors for programs. It's not necessary to do that. You can do outside the shell, and then it's easier or even LibreOffice or something like that. I use Vim because I started with Vim many years ago also. The program I want to show you is this one. It will be uploaded just after the class. I wanted just to show. Oh, so can you read?
Yes.
You can. Oh,
Yes,
perfect.
okay.
So this is a structure of a typical example of a system call. Of system call for doing what? Not for communicating between processes, but just the first thing we'll learn. How to run a new process by a process. So you see that in the middle of the screen, there is the main program, the main is running. We have a function in the same file that is called char at a time, that is used for outputting a string. And there are some includes. Those includes are the includes necessary for the for system calls and for any kind of group of system calls. There are special includes, but it's very simple to decide what is necessary. So we concentrate on the main. We use so it's a pure C language, and you see also that we use the printf instead of cout in a C++ fashion. We use a put char, so pure C language. For me, it's simpler just to interface the Posix system calls. And typically, we use the interface to the program with argc and argv that we will use in every exercise because we want to run the program with some changing parameters during the execution. And this is the way of having a program that is a sort of dynamical linking. Or in that case, first, let me comment the first lines. It asks if there are two arguments. Remember that if you have one argument, only one argument to the, when you run the program, the number is 2, because the first argument is always the name of the file, the executed file. So in that case, the usage, if you don't 2 arguments, you have a message that you must use pp. pp is the name of the executable that we will generate with a number, pp 10, pp 1000, pp, we don't know. And the number is the number of nanoseconds of delay inside the loop. So the argument is taken with the, as the argv position 1, and since the interface with the of the standard C-language standard interface returned strings is converted with the A to I into a integer number and assigned to delay. And then the first system call, fork. Fork is the simplest way of running a new program, a new process. It's called fork, and you will see in details, but now on is just to see the concept and also an impression on what is Posix programming. Fork gives back a value. You check if the return value of a fork is 0. If it's 0, is one process. In particular, is the same process already running. So the nesting and indentation is not important, of course. I've done that just to put into evidence the 2 processes. The else part, so if the return value of fork is a system call, the return value is not 0, we don't know what it is, but you will know it's important, is another process. So just after fork in the operating system, if you remember the slide, there are 2 processes. Until you call fork, there is just one process. The process you have compiled and is running. After fork, there are 2 processes. The 2 processes are equal, so are cloned. These processes are completely identical, 2 copies of the same. So just how you can distinguish which is the first one, the one who raised the process of generating a new process, and which is the generated process, just the value returned by fork. If it is 0, it's the same process. The new process has a value that is different from 0. So the 2 codes after the if else are the codes executed by the 2 processes after the fork has been executed. Simply that. So after the 2 processes they can do, of course, the different things. In that case, each process, the original in jargon is called the parent, and the new process jargon is called the child process. Both call the function shared time, but of course are 2 different calls. As just like the shared time was in 2 different copies. The parent process calls sending as a parameter the string 1111111. The second process, the child process, calls shared time with the string 0000. The second parameter is a delay. So let's go inside the shared time. Shared time simply gets a string. You see the old-fashioned parameter char star string str you may use a char array inside of a string point, a char pointer, of course. It's just the way you prefer. And the char at a time is an endless loop. Well, it's not endless. Is scans all the elements of the string, and they output, and it outputs the element of a string. Written with the array may be clearer than using the pointer version, but I assume that you are able to translate, if you want, or to decode, to understand the pointer version with respect to the array version. And one by one, the char at a time puts the characters on the screen and write. The F flash is another system call that assures you that after carrying out the put char of any character is really put on the output window instead of being buffered. So you see immediately. F flash is typical, and we will find many times, because also in when we write, you remember the log file, we need to flush immediately to be sure that no buffering inside keeps the datum and is not physically written. In that case, physically written on the screen. And then you sleep. You sleep. We will use sleep many times, just for simulating the time required by the external world. The sleep just is a family of primitives. You sleep as an argument of nanoseconds, so it's very fine function, and suspends the process for a given numbers of nanoseconds. Suspends, and so it's a system call that simply raises an internal software interrupt, and all the process we have described. We have described all the process. The switcher puts the process in sleeping state because it waits for an external event to resume, and in particular that at least d nanoseconds has passed. This is just to make the execution slower. So in this case, it's used as a trick to make it slower than normal execution. So if you read this, what we expect that happens, we expect that after we run the main, saying, for example, sleep 1000 nanoseconds, so 1 microsecond, at least 1 microsecond, so it depends on the kernel. You expect that after the fork, there are 2 processes, each one simultaneously, concurrently, outputs the string. So one process, the parent process, outputs 1 by 1, 1, 1, 1, 1, 1, 1. The second process is outputs 0, 0, 0, 0. At what speed? The speed determined by the delay of the use sleep. If you put a lot of nanoseconds, they will go slower than if you put many slow nanoseconds. This is just an example, just to show also the effect of a concurrency. Concurrency in that case is a concurrency achieved with the time sharing execution of the processes. Well, now we compile just to have a real exercise and to do all the phases for your exercises. You have written this code. Now we will compile and see what happens and execute Then we will have a look to the lower lines, there are comments, there are assignments for you. Even if you don't know yet exactly what is fork and other things, you now with this explanation you know enough to do the things that are asked to you in the end. So it's also an assignment for next week. Okay, this was we don't change anything inside, so we exit from the editor. I don't suggest you to use the lowest level, the oldest editor like Vim or VI. I suggest you to use the normal editor, visual editor in Linux, and to save the file and use. But if you want to go back 40 years, you can use the old style editor. Well, we compile. Depends on the compiler you have. I suggest you to install GCC, or probably is already installed in the Ubuntu distribution. GCC, GCC. I want to generate an executable with the name pp. Okay, I did, because if you don't put the -o, that means minus output, the name of the file to be generated, the executable has a standard name that is a.out. It runs in any case, but you have just a dummy name, and you cannot have several executables except that. So I suggest you use pp. If I do, well, to run this, unless you set some environmental values, you must say the pp in the current directory. So /pp. If you say this, of course, pp discovers that you did not issue a second number, the argument, and comply and says, okay, use pp and nanoseconds. Then pp, let's do something like, okay, what you are seeing, you see that the string is not uniform. Maybe someone of you wanted to see 0, 1, 0, 1, 0, 1, but in some cases, you see that there is a couple of 1 and a couple of 0. So it seems that the execution is not, what can I say, uniform. It depends on the speeds of the two processes, because this is the concept of concurrency. You cannot foresee the speeds of the two processes. If you do the same thing, delaying this case, you see, in that case it's more uniform, because the scheduler has scheduled the two processes in a more uniform way. So the switcher had the time to, more than in the previous case, to switch from one process to the other, but not always. It's very difficult to foresee what happens. If you do something like that, so in practice, no delay, every time it changes. And if you try this with several delays and see the difference between and how it is not, you cannot foresee exactly what is the result. If you load the system, I don't do that because we have no time, and I think the class is over. For example, running many other processes, you will see that also something changes, and the sequence in which the put char are executed changes in a way that you cannot foresee. So it's just also an example to show the concept of asynchronicity and non-determinism. So we have simply run two processes, but we have no control on the sequence of execution of the instruction of the single processes. That was the main idea. If you look at the assignment that I have written in the bottom, you are asked to try and to slightly modify the code so that to achieve a sort of synchronization between the two processes, but in the future we will see which is the correct way of synchronizing them. For example, it is suggested to find a way of making the output to be, for example, 0, 0, 1, 1, so couples of characters. Can be done in a rough way, and we will use this example in the future in other describing other system calls for doing that, because synchronization of processes is really important in automation and absolutely important in robotics. So these are just the first steps. I wanted to start softly, in a soft way, because not everybody of you is a good programmer, has a background in C programming or C++ or Java programming. So I wanted just to show an example and try to put your hands on this example, modifying with the following this, the requirements and the suggestion I put on top, on the bottom of the code. So next week we will finish the description of the kernel, including the how are exactly the processes and which are the structures of the processes that are necessary for understanding the old system calls, and we will keep on the schedule of the program that you have seen. Okay, questions?
Yes, Prof.
Yeah.
Have you uploaded the complete slides on robot programming?
I have uploaded the slides of the Linux architecture. The first pack of slides is already uploaded in the previous week, but there's a link also in this week. And just at the end of the lesson, I will upload also the new pack that I will ask you to read before the next week, so we can comment them, and also this acceptor program.
Okay, thank you.
And obviously the recording. Okay?
Professor, excuse me.
Yeah?
When were you talking about priority behavior? You have talked about nice command. What do you mean with nice command?
Oh, nice command. Nice is one of the commands, and as a counterpart, as a system call that you can issue using the shell, the Unix, the Linux shell. One of the command of the shell language, interface language, is nice. So when you run a program, for example, instead of running the PP program, just simply typing the name of the executable, you could run nice PP. Nice PP, nice with the number, and giving the PP program an initial priority different from the standard 0 priority. All shell commands are commands given to the shell interface, but shell is also a programming language. So single commands I will show in a next exercise using the shell. When you issue a command, a simple command in shell, just like running a program or ls listing, these are commands to the shell that are keywords of the shell language. One of the shell commands or the elements of the language is nice. Most part, not sure that all, well, most part of the shell commands are also system calls. Okay, long answer, but just to introduce some other concept that is important for programmers, for system programmers, that shell is a language, and many software are distributed in with the shell program.
Thank you, Professor.
Okay, I think it is over. Thank you very much. See next week. Stop recording.